Hi, this is lecture 16. We'll finish up chapter 10 that discusses lastly about squeezing deformation, and then move on to chapter 11 where I will first give you an overview about what to see in melt extension, and then focus on the controversy regarding different ways to examine melt stretching conditions.
We're in the middle, toward the end of finishing chapter 10, which are just a place where I illustrated some special cases for shear bending for you to have what you have learned from wall slip to shear bending in simple shear, and you anticipate, as I did, that this could also happen in more complex geometries, such as at the entry of a die during extrusion. We went through that in some detail last time and emphasized the theoretical meanings of having such observations as we did in the other apparently in the other PPTs. So I will not further remind you of that, except to give you one more case within chapter 10, and that's the case of squeezing. So in chapter 10, we funny enough, finally the pen disappeared. Let's see if the other one has it. Anyone? Gosh. I previously played the trick and click here, the pen would appear. This we never encountered before. Happens. We don't have enough chance to practice when this happens, which never happened before. I doubt it, because I just disabled already. Oops, sorry. I just disabled it already, so I don't know why. Gosh. To turn on. Turn on, I will get to right. That's probably okay if I cannot get it back. And we will, I think there are issues about where to find erasers, and now I don't know where the pen is actually. Here comes back. See? Sometimes I also wonder whether there's some correlation between the two. I don't think so. But it's back. Okay, sorry for this. So in any case, we are, I'm going to just give you one more case of showing you that within this different examples of non-uniform deformation. I'm giving you one more example of showing you building a device where you have a piston pushing your material in here out from the two ends. And if there's no slip boundary condition, this material will come out with a parabolic kind of, you can expect it to come out like this. because of no slip boundary condition. And so in principle, you could make the sidewall transparent so that you can, and also the bottom transparent so that you can shine a sheet of light, laser like that, and have camera watching into it. Okay, so that's what you have. And this is the type of movie rotated 90 degrees. So this is the piston coming in and pushing the material. And this material is also impregnated with light reflecting particles. You can see that there is a great deal of slip, as you can see, as you start to squeeze. See that at the wall. In fact, if there is no slip, it will be all stationary at the two walls. So this side, the left side of the wall is moving in. So this is again just sort of in anticipation that something may occur in a manner that's not expected. In other words, in absence of slip or any shear banding, you would expect this to be parabolic. So this is another one showing a little more obvious case. Look, this field is clearly very different than what is a parabolic shaped field. And this was done actually by pushing with a constant speed. Constant force. This was just done in a way that the force was pushed at a constant value. And then you just watch how the material undergoes squeezing. Okay, you can see that the side is moving faster than the middle, which clearly is a symptom of something failing, if that's happening like that. So there is actually one article published on this geometry. So the chapter 10 had a part describing squeeze because there was the desire to squeeze, as I shown with this diagram. There was a desire to examine our predictions about what happens. And that's why this was discussed, although the paper was not out at that time. So this paper came out after the book has appeared. So later, I will give you a second case where this geometry is used. And we published a separate paper describing how useful such a technique is. In fact, the huge reason for using this geometry is the following, that because we heard plenty of complaints, which I didn't say too much, about whenever you observe shear banding, complaints, I mean, I'm using just a casual word. There are people who are explaining that this shear banding results from edge instability, which I don't agree. But, everyone have their own opinion and scientific view about it. So the device like this was an attempt to eliminate the meniscus. You see, in a simple shear, you cannot eliminate it. We have a film wrapped around, but still, it is a boundary that is difficult to control, to claim that the boundary has nothing to do with what you observe inside, okay? Whereas this one is different. This one is you build a trough, right? You build a gap like this with two side walls, and you have your piston fit into that gap, pushing a material sitting at the bottom out. So the only place you do have free surface are these two opening points where it comes out. So as you push it down, the sample becomes thinner, and the material pushes out from the two openings. This geometry is totally basically eliminate all the free surfaces, because this two free surface is exiting, so it does not matter. It doesn't affect, yeah, there. So this is a very peculiar way of designing it. There are several terms you can use it, but this particular geometry, because of two side walls, your sample width does not change. The W does not change. Your sample's height is translated into length. Length in the sense of exiting from the two ends. So the area is fixed because your L is fixed. So it's a peculiar situation. You have to imagine your L is keep increasing because it's being squeezed out. But you only examine a section of the sample that corresponding to a fixed surface. Yeah. The key is you eliminate any complications. Nobody on Earth, nobody, not even people who are explaining shear bending with the edge effect, can tell them that this thing exiting will affect what you see here. Okay? Nobody. Because this whole thing is exiting out. There's no chance for any propagation of the perturbation that's happening here. So that was the real desire, to eliminate any complications and still show the physics of strand localization takes place, the horse race. In other words, what you observed here is quite remarkable. I mean, the zero result example is really like a wall slip, but you can see here, look at this part. There's something that's going on. The paper is described in detail, but basically it's not a parabolic shape. And that is because the force you applied was high enough. Okay, so this force, through the analysis in chapter 10, as well as chapter 5, when we discussed, I omitted all this. When we discussed this geometry, this force can be all translated into a shear stress through the mathematical formulas. So when the force is large enough, you are applying a shear experiment in the limit of, it's like a creep because it's a constant stress experiment. And just like you observed was a stick-slip transition, when the stress is high enough, you could undergo wall slip, which you saw here. I keep saying wall slip because it will come back again, wall slip. And I just want to emphasize that this movie can never give you a proof of wall slip, because wall slip claims to involve only one monolayer of disentanglement. Our particle tracking velocimetry never have that kind of spatial resolution. So we can only say it looks wall slip-like. And I just want to repeat, the only time you can be confident that this is only wall slip involving one monolayer is by theoretical calculation to show the magnitude of slip. Again, this is something I prefer to have more casual discussions with you than being more formal. If you read every line in the book, every point I'm talking about is covered. Just at the point, there are times that I'm somewhat sketchy. Okay, so So this is just another example of a prediction, of envisioning what could happen, okay? And I can be fairly brief, and we are more or less done with it, except to mention that this is a geometry that doesn't have a particular name when you have no lubrication. So the sample is establishing some absorption with the piston and with the bottom surface in the limit of no. I just see myself plotting the wrong part, right? In this plot, this is our piston. The sample is only here. So the sample here is doing parabolic. Okay. So in the limit of no slip, it will perform like this, parabolically. Therefore, you can see that it's largely shear. But the detailed mathematics show you actually there is also a small extensional component. When you have lubrication, I just want to mention, when you have lubrication, this has a particularly well-known geometry or a name for it. It's called pure shear. Because if I establish this as x, y, z, then my lambda z is essentially 1 over lambda x, and lambda y is constant. In other words, the width doesn't change. And my decrease in the gap, it's a funny choice I had. I had a gap height as z. So the decrease in z is a result of lengthening in the x direction. So this is called pure shear. And it's rather confusing. This is also known as planar extension. So there are two names for the same deformation geometry. Planar extension because it is extending in the x direction at the expense of the thickness, keeping the third direction constant. Right? So it is an extension. Any questions on this? So it's just a very brief introduction in that sense. It's a geometry that could be useful depending on what we do with it. Okay, let's move on. Because there's still a lot to talk about before we run out of time. So let's move on to chapter 11. I hope to get a lot of your participation in this chapter because it remains highly controversial to some degree. And it is, I'm not saying all the chapters are core chapters, but this is one of the key chapters in the book. And this is, in your mind, should remind you that it is the parallel to chapter 9. In chapter 9, we dealt with shear, strain, localization. That's a fancy word for localization. That's a fancy word for shear banding. And we saw plenty of it through the so-called particle tracking velocimetry. And as I indicated, that as soon as we had movies showing shear banding, which means we will have to understand why it happens. As soon as we understand the physics behind it, behind shear banding, we realize the same physics should occur in extension, okay, which is, you may say, more commonly demonstratable, or easier to demonstrate. Extension, you just grab something and stretch. And of course, in processing, that is a very essential way of dealing with polymers. So this chapter 11 is basically the mirror in parallel of the case of extension. Of course, extension has two parts. One is you can do it uniaxially, which is having a piece, just keep stretching it on two ends. Another is biaxial. It requires a little more specialized device, basically imagining stretching in both directions such that the area increase eventually leads to a decrease in the thickness. So that's biaxial. There are industrial machines for making the product, or also in lab scale. One could imagine grabbing such a sample, such as a square sheet, and stretch in both directions, either simultaneously or sequentially. Since this is a more complicated geometry, and since the physics is the same, presumably, we will demonstrate mostly, we'll study mostly this uniaxial case. When we say the physics are the same, I had a small sense described last time. What physics? The physics of chain disentanglement. The physics of that chain disentanglement leads to microscopically observable yielding, right? The microscopic quantity, such as stress, start to reach a peak, right? Overshoot. And start to come down, right? So that's the phenomenology, if you like. So when that happens, there is a chance that this happens not uniformly, and because this process could be a horse race, right? So that's the physics we know so far, or at least it makes sense for us to interpret what we observe in this manner. Remember, nobody needs to be convinced without evidence. You could have your speculation. If it's a different one, that's fine too, right? So what we anticipate is that this scenario should also occur in extension. So in extension, that we're going to focus on from now on, chapter 11, you can see it's a simpler task in the first place, technically. It's a simpler task because you don't need to build particle tracking velocimetry per se. It's in front of your eyes if you manage to do that. But I told you that people do shear, don't do extension, and vice versa in the past until the man invented a device where you can put your sample fix your sample onto the two rotating drum, and this is through some device is connected to your rotating rheometer, rotational rheometer. Until you have something as convenient as that, it's still not easy to do extension for the folks who only previously do shear. But now you can. And this device was essentially, in fact, there's a very important contrast I must right away indicate. This device was built, you see, for example, the cylinder that has the dimension of d as diameter is in principle for you to choose. I mean, for the same scenario, you can imagine I have cylinders this big versus this big in diameter. The man who invented this, he invented this at Goodyear by choosing appropriate D on the order of about 10 millimeter or less, such that by calculation, you see, the diameter, of course, determines the torque. And torque, of course, is what you have as your specification in your rotational rheometer. For example, the torque in a commercial rheometer is 0.2 Newton meter. Okay? So so this guy who knows what he wants to do, he wants to use this device to examine, let's say, a elastomer. So he knows exactly what the stress level is required. And therefore, he come up with a dimension of 10 millimeters. Okay? So with this device, even when you are dealing with melts, the torque that arises due to stretching a piece between the two drums is not going to exceed the limit of the rheometer. What does that mean? It means something remarkable that I always remind myself, that the commercial rotational rheometer can hardly handle melts for two reasons. If you handle melts, typically this diameter will need to be as small as less than 10 millimeters. And that's getting very small. When it is that small, the edge instability is very severe. Okay? So, in other words, in shear, we hardly can handle melts, no melts. But in extension, using this invention, the same rheometer can handle melts, just because of the design. So this piece, for example, will have an initial width of, let's say, 3 to 5 millimeters. And the thickness you can adjust so that you can satisfy the torque range. Okay, so I just want to get you the mechanics part right, that, that we are lucky enough by the time we recognize the same physics may apply in extension, okay, is the time people have just invented this accessory. or rotational rheometry. So we can get hold of it and examine whether what we expected is true, the same physics, or what is different between shear versus extension. Okay? And so I hope this is all clear. So I further want to emphasize it's a simpler task, right? Because there's no need to build anything to observe. What's happening is in front of you. Because of that, and perhaps because of that, we actually know a lot about extension prior to we getting into this to understand the physics of it. So it turns out prior to us getting into this, let me see how much of a chapter kind of thing I should follow. I'm right now still just giving you an introduction, okay? Just the introduction before any sections even. So, as I said, this is about the uniaxial extension. As I said, you don't need to build anything. And as I said, or if I haven't said it yet, one, of course, in the past have had Ingstrom type of device. Basically, it's a stretcher where you can put your sample in between two clamps and start to move your. Usually the base is fixed, then start to move one of the clamp. So in theory, you can achieve extension. In particular, and this is why the Russian group did this. In particular, if this sample is rubbery, in fact, rubber kind of polymers, for example, polyisoprene, SBR. I think polyisoprene is particularly attractive to do. Not what? Not polyethylene. Because polyethylene, you have to go above TM. Once it's above TM, polyethylene almost falls apart. It cannot have much. TM is, let's say, 120 degrees at least. TG is minus 100 for polyethylene. So it's challenging to do with polyethylene in a Ingstrom. And if Ingstrom, such a device, is the only thing you have, then get hold of some rubbery polymer. Rubbery polymer, if you know the Maxwell relaxation time, the tau can be 10 minutes. So in other words, it's not going to flow and fall apart very quickly. Okay? So for example, that Ingstrom can hardly do this PDMS that I have here. Not easily because there is a gravity that will cause the sample to change. You know, and it's so soft, it's hard to hold it. So in any case, the Russian group, particularly Vinogradov group lab, have made all kinds of observations when they get hold of rubber and try to stretch. So one of the review paper was published in 1997. That's before we ever, remember we got into observing shear bending. That's the 2005-06 already. So they have observed, and they made the following observations, which is the first figure that I can show you there. Basically, they get a hold of rubber and put in some kind of device and start to stretch, okay? And the key finding they have is that they find, as I stretch, let me just use this PDMS to demonstrate. This PDMS, as I stretch, let's say if I I'm impatient to stretch quite fast. Oops. It's separated into two pieces. But conversely, if I'm very patient and able to draw it very slowly, well, actually, I'm demonstrating it very slowly because this tau is quite small. So slow is very easy to achieve. So you can see it draws quite nicely. Okay? So there are regions, region 1, where you're drawing with WI smaller than 1. Then the place it breaks, so if you call that breaking strand, is very high. It's very, very high. I'm not going to go into details how high it is. And of course, Weissenberg number is just Hanke rate times relaxation time. Another beauty about playing with rubber is you can make them monodisperse. Polydispersity index can be very narrow, very small, unlike polyethylene. So you can have better, well-defined tau, for example. Okay, that's just a side point. So as I showed you, in that limit, the sample can stretch a great deal before it breaks. And then there will be regions, right? Oops. There will be regions that's above WI equals 1. So there will be a region of, let's call region 2, where you find that the sample, oh Lord, this calibration occurs again. What do I do? I can only stop it. Christ, what they are doing. Trying to save. Sorry about this technical part. It's not the pen is not where the screw. Okay. Once I save it, I have to reopen it. This should fix the problem. Okay. So there is a region where it tends to break quite early. How early? I'm not giving you a number here. As early as Hanke strain equals 1. Hanke strain equals 1 is lambda equals 2.7. And then for the very same sample, you can start to stretch at a higher rate. And it becomes more stretchable again. When I say stretchable, meaning before it fails. So you enter region 3. And then there's also a region 4. so there are basically 4 zones. And this region 4 typically involves Rheometry number as large as 10. Okay, I know I'm doing this interchangeably. If you like this, it will be like 30Z. Because Rheo's relaxation time is tau over 3Z. Okay, so I'm just trying to first give you what is already known. There are 4 regions. And the bad news first is a break in all of the cases, except region 1. I mean, if you patiently do it, the only time it will break is through some capillary instability, the surface tension kind of related. And that's not what we're interested in. In any event, when the stretching is in the non-linear region, the sample break following these the red the red curve describes where it breaks. And I think there's nothing better than giving you a sense of the data. Here it is. It takes me so much time to write it, but to describe it, but here they are on this page. So there are 4 regions, and in fact, probably a more accurate way to draw is what I did in the book. And here's the raw data. Basically, this high, so what's plotted is the engineering stress as a function of lambda. And these few black symbols are the high stress. That's region 4. And we'll describe this in detail, what happens there. Region 4, which we call the rupture. And then at the lower rate, you find your sample can stretch by a factor of 20 lambda before any observable failure occurs. But as you reduce the stretching rate to lower value, you find your samples start to break at earlier and earlier lambda, smaller and smaller lambda. As much as you can see, it's only lambda is only 3 or 2 when it breaks. Okay? So this is all quite mysterious. It's mapped out by basically my friend Malkin. This is the paper, Malkin and Petrie in 1997. When I was in a very early stage of investigating this, I had several email exchanges with Professor Malkin. And he was very casually describing these failures. He says something like, oh, at the low rate, like region 2, it ruptures very sharply. I could never understand all these, what did he mean by that. But the communication and the sense I get indeed is that in different regions, the failure behavior is very different. Okay, so today we firmly establishes or agrees with what he observed, that there are 4 regions, and I'm probably going to be somewhat sketchy about the details. So here's what I do for this course, and for any very, very detailed stuff, I just leave it to the book, And at your leisure, you can read the book and find all the details. I'm just going to point out the less obvious things from reading the book and somehow emphasize the essential part. So for example, regime 2, yeah, the sample breaks very abruptly. I mean, here's just from the book, here's the example of regime 2. This was a profile that was done by using an IR camera. It's just to allow us to track it more easily. In other words, as you stretch, it turns out your polymer melt actually heats up a little bit. And this is a rubbery polymer. So you can see when you first stretch to this point, it's uniform. By the time of 2, you can see a hint of what is giving the disaster, meaning it's no longer homogeneously stretching. And that's only lambda of 3 or so. And then the subsequent failure is quite sharp. Just around here, it will break. Okay? So that's just one example of what I, in the book, carefully called this regime 2 tensile decohesion. The physics of it, we can probably come back after chapter 16, after the theory. We can come back to this, discuss about the physics of this a little more. What I want to do to bring your, no, to get your attention, it is something that remains quite a challenge or confusion still in the literature. So what I want to do is this, is that, look, you take an Ingstrom, you grab your sample and do it in different rate, you find, so just to be consistent with the book, I think the book is more careful than I did try it. Oops. I could call this regime 2 really is beyond that. So let's focus on the important part. What is said is in each of these regimes, the sample break. Russian data have shown that. We subsequently have seen the same. Okay? And of course, you can ask, hey, why did it break? Well, the short answer is disentanglement from a horse race. I see that I think I could almost recall, but basically in this paper, it's about the phenomenology. It was very little was about understanding the physics of this. For example, let's get to the physics of this. We shown, right? Oh God, why did I shift it so much? Yeah, here we are. This is not the first time you have seen it, but it's only maybe second time. When we do a startup extension, I discussed with you a good way to appreciate what the response is to look at the engineering stress, okay? Which is the force divided by the initial area. And you see that there are maximums in them. And I hope, I'm willing to repeat, but we can go to the proper recording and chapter to find out what I said. The peak is an indication of yield. the peak in the tensile force is an indication of yield because if your sample would remain entangled, your force should keep rising. Remain entangled, then I can use this formula to describe the engineering stress. Remain entangled means I can borrow a rubbery-like formula. Since each of the strands in my network is keep stretching, so of course this term keep growing. So the only way this quantity could decrease is I start to have a softer material. G is modulus. And the only way to have a softer material is if you start to lose entanglement. In other words, instead of having 3 strands, you will start to have only 2 strands resisting the stretching. So this is, I'm just repeating. I really need you to be with me on this. Otherwise, you can go to the end part of chapter 7 to find what we said about the fact that this is yield point. And we even proved that if you stretch it up to that much before the maximum and let go, it will come back, whereas after that, it will not come back and let go. So this is clearly, this maximum clearly have a similar meaning to the overshoot in simple shear, startup shear. And we know that this softening is a result of disentanglement. What's left is to understand how this disentanglement can occur uniformly or not. And remember, you have how many horses? 10 to the 1,000,000 or several million horses. And each of the horses are very much similar to the case of shear. They are all communicating with each other, except in extension. If one horse fails to untangle, then it fails to be able to transmit the force to the next. So it's quite natural that the sample could, through the horse race, could start to fail at one point. Once the failure starts to occur, there's no turning back. And in what we learn, the B over H kind of criteria does not exist in extension. So this horse race just cascades. It's like an avalanche. Once it starts, the argument of it does. Remember, I even had a great deal of a comment about considerate criteria about necking. This disentanglement could continue for a long while, and at some point, the structure is just no longer able to sustain itself, and some part will start to fail. And depending on regime 2 or 3, this could occur very early, near the peak, or very much after the peak. That's the difference between region 2 and region 3. I know there's a lot of details. I'm going to skip it. The key emphasis is that the disentanglement will cause you to lose the ability to stretch your sample uniformly. In other words, the sample will break. I know I have repeated this message so many times now. So, in short, in conclusion, well-entangled, well-entangled melts undergo tensile failure if I choose just a general word. Of course, really what it means is a strand localization. In other words, uniform extension ceases at some point for all values of Weissenberg number larger than 1. This is an experimental observation. It agrees with the fact you have inhomogeneous disentanglement. And the inhomogeneity comes from the fact that there is a horse race. And this actually caused the experiment to terminate. And this is the part that's a little bit cute. It caused the experiment to terminate. If you recall, in the case of shear, you can have shear banding that it does not terminate the experiment in shear. You just have, one shear this much, the other one shear this much. They happily coexist. The force, the shear stress transmits across. The top layer sheared more. You just need to shear more to produce the same stress as the layer that sheared less. But nothing terminates. Nothing terminates. But in extension, bad luck. There's no chance. There's nothing that, because I like to think that the load in extension is in series. So there's no way you can continue when one element fails. Okay. Why do I say all this? Because it seems a great number, or maybe a majority, does not believe this in this statement. Okay? Does not believe in this statement. So this is the part I want to focus on. Before we come back to describe I will come back to describe region 4. If I run out of time, we'll describe it next time. But for now, the message is clear that there's no way the sample can and therefore cannot attend steady flow state. Okay? Of course, you say, oh, what do I mean by steady flow state? Well, if you look at your engineering stress versus lambda, okay, then the steady flow state will be a state where eventually your engineering stress will go with lambda as 1 over lambda, because then your true stress would reach constant, right? So I claim that such polymers under this condition cannot achieve that. Well, because it broke, right? The sample break apart. Okay? This is what we observed. And we think we understand why it fails, because it breaks, because it disentangles. And then we have yet to, of course, say about the details about why it would disentangle. But this is the phenomenology. But just this phenomenology, meaning just this set of observation, is not agreeable by others because of the following confusion. This is a debate that's still ongoing. I mean, this is certainly the part that makes me feel, you can say, motivated or cheered up. So let me talk about this particular section. So after introduction of these 4 regimes, I want to jump to a key part of this chapter, which is the last part of it. In other words, can we claim steady flow? Since I posed the question for you that it cannot, but so why people think you can? Right? I just showed you cannot. So let me describe this part. I hope to get your involvement on this. So it turns out there is a separate. So there's this, if you like, Russian and many others. I don't want to get there are many others, including our late Professor White has done work on this. Many others. Basically, they take a Yingström, and as I showed you, it was able to find, gosh, let me not be so casual on this. And they were able to find that there were different regimes, if you think about the failure. So basically, reporting failure. Okay, reporting failure as a function of different Hanke rate. So that's one part of the universe. There's another part of the universe started indeed as early as 80s, if not even earlier, where in particular, in the beginning, this could be solutions. And you see how nice this is. In other words, if I actually already mentioned to you, so this is dealing with rubbery polymers, basically polymers that you can sort of grab it and stretch. Okay? It has enough temporary solidity for you to grab it and stretch. And I already showed you last time, if your samples are liquid, I showed you that, I think I did, that you can, if you have a liquid, you may think about put 4 cylinders in your liquid reservoir and try to turn your 4 rods like that, and that could produce an extension like that, okay? Right? And even simpler, I showed you that you can have a wall and just push your liquid, just shoot your liquid onto the wall, and that tends to give you a shear extension, okay? But of course, in the second scenario, it's hard for you to make any rheological measurement, right? Of what is the force and so on and so forth. But in any case, you can see that when you have a substance that you cannot have integrity to grab it, then of course this Russian way of doing it, the Yingström way, I call it, of course won't work. So let's do it another way. So that's why people started this way. Let's have a sample that's liquid-like put them in between 2 circular disks. Because of surface tension, it will not flow out. And then turns out by design, it's always easier to hold one fixed. And then what about just move this upper one upward? Why not? So it turns out this doesn't have to be solutions. In theory, this can be melts. You just need to melt it in the molten state, make sure polymer absorbs to the wall. And then there are two disks, you just grab one of the disks and try to pull. Okay? So a later moment, this sample will look somewhat like this. Okay? A later moment yet, the sample may look. I try to use the same size, it's about this long, about this wide. A later moment yet, it could be just. I know I'm not doing the best I could, but something of this nature. Yeah? So what happens is your cross section is shrinking like this. Probably I can do better after being guided by this circle. So basically, you have something like this. And you can be quantitative. You can find a way to measure the middle, the diameter in the middle, as a function of t. As a function of the speed, you're stretching it. I mean, speed being v over L. And of course, this is your L. Okay? And you can even make sure that this is done with a constant Hanke rate. And you will find your D will just decrease as because the area, which is d squared, is nothing but 1 over lambda. And that's nothing but minus epsilon dot times t. Or that is nothing but minus epsilon. Or this just shows, I'm just repeating to you that the relationship between lambda and epsilon is this. Right? So nothing fancy. Basically, you can put your sample in between parallel plate and stretch like this. Okay? What's different compared to this way? Compared to this way with the Ingström holding the samples. What's different? Or I probably should ask you differently. What's different if I tell you the way I perform the experiment on the left, keeping this condition, is I make sure that my diameter changes with time like this. Right? Because if it does so, then I claim that I'm doing uniaxial extension. But since on this, remember this is world 1, this is world 2. Since in this world, you learned that this sample at some point will refuse to stretch uniformly. Yeah? One part will start to break. Yeah? One part will start to break. Yeah? Do you think in this world 2 that the sample will also tend to break or not? Yes or no? Similar rate, similar whatever. I see some people say it should. So let me just give you a sense, then you will start to appreciate the difference. So suppose I can monitor this and make sure my diameter is shrinking exponentially like so. How do I make sure? I'll make sure my speed here is such that this is guaranteed. In other words, there is a feedback loop between them. I will adjust my V to whatever value such that this remains true. But my question to you is, are you going to see the same world or not? Have I confused you so far? The question is, there are two scenarios. I'm examining the same sample with the same Hanke rate. I at least claim, at least as far as the middle is concerned, it's the same Hanke rate. Well, what difference would you anticipate? We know on the left, on the right, the sample will fall apart, right? Will break. What happened to the right? I mean, what happens to this actually has a name. This is called filament stretching rheometry, or rheometer, whatever. FSR. This side is, I call the Ingstrom, but with that double cylinder, we have a name, we call it SER. S stands for the inventor's last name. E means extension, R means rheometry. So I'm presenting to you, in front of you, two scenarios, SER versus FSR. Yeah? Yeah. Yes. The other one just fails. Yeah. I prefer you say it more carefully. So we start with on the right, SER, we start with a constant Hanke rate, and if you're trying to maintain the Hanke rate by, of course, having V over L being constant, right? Same thing, but you don't have monitoring, right? You don't monitor anywhere else. At some point, so here's the same game. This condition is the same as when you do shear and close your eyes and hope there's no shear bending. It's the same scenario, yeah? In other words, what you are dictating is just the boundary, if you like, right? Because You can only hope that your sample behaves properly. Everywhere will stretch the same amount. But just like in shear banding, it doesn't. It breaks. This requires you to hope that your deformation is homogeneous, right? And what I just indicated in here by the summary is they never does. Up to some point, after some point, it will break. So on one side, I conclude sample will break, although you try to maintain homogeneous deformation. It happens for a while, and then it will break. On the left, you just properly made a guess that I'm going to continue and adjusting my V as long as I can maintain this diameter change, right? So that's clear. What is not clear is the following simple story. Your sample presumably would, at some point, I don't think anyone need to debate with me, will try to undergo disentanglement, okay? Let's say. And it will try to break up, okay? This device basically is taking that breaking into account, right? In other words, if the middle trying to break, shrink, you will slow down. Okay, you get it. You get it. You didn't read the book yet. Yeah, so that's exactly the point. You just slow it down. No, there's an electronic feedback loop. So they just computerize it. If you see, this is the key point. The sample will have a tendency to break according to the word 1. But as soon as it starts to have a sense of doing that, my sensor is monitoring that's going to happen. Oops, I will slow down so that it doesn't break. It so precise. It looks like it will not break. And indeed, it tends not to break.
So if you are stretching the sample, then the L will be changing. So
the what will change?
then it will be longer.
Yeah, sure.
So how do you, so if this gets longer and the velocity is constant, will the
No. Sorry. So you caught the point already. We're keeping this constant. So when L gets longer, V also gets faster. So that to keep it constant. That's the key. So if you hear that sample, the motor is slowly it's doing that.
This is the same case for the other solution? The velocity is also changing here?
That's right. Except since you ask. Except that's the beauty of this device too. You see? It's wrapped around two drum and stretch. This L never changes. And therefore, your V does not need to change. In other words, the rotating cylinder is at a constant speed. So you have to imagine you just keep watching the middle part. Imagine you do an experiment in strong, like you did here. And you block everywhere else, just watching this part. Since this part involves a fixed L, then you will see the velocity coming from that point is always the same, right, by definition. Although the end part is getting faster and faster. Yeah. Okay, actually I want to stop this. I know we're running out of time. I can just stop it here. And then we can go to the question section if you like.